Good morning friends. On the demand of student, today I am uploading lecture on vibration. You can also discuss with my book written on vibration and noise harshness published by Engg Publish. After the end of this lecture, student will be able to explain definition of vibration, scope of vibration, vibration phenomena, various terms used in vibration analysis, degree of freedom, vibration systems, types of vibration, motion considered in vibration analysis, and simple harmonic motion. Let we start with definition of vibration. Vibration is defined as self-repetitive motion after a time interval. Example of the vibration: swinging of pendulum, next topic is scope of vibration. Two scopes are considered: in which first is your study scope, second is application scope. In this study scope includes harmful effect of vibration, and in this application scope includes use of vibration. The various harmful effects in study scope are looseness of parts, due to vibration, leads failure, unbalanced force leads to failure, unpleasant noise leads to noise pollution, and error in measuring instruments. Due to improper reading. These all are included in study scope of vibration. In this application scope, we are using the vibration used in musical instruments. Used for efficiency increasing, in casting, forging and welding, used in equipments like vibratory hopper, and next is used in stress relieving. These includes the application scope and these includes the harmful scope. Next topic is vibration phenomena. Vibration is to and fro motion about its mean position. Let us considering a pendulum as shown below. If we are giving some disturbance to this pendulum, it will start to vibrate along this axis. This position is the peak position and this position is the mid position. At this peak position, the kinetic energy is 0. At this mid position, potential energy is 0. This is an example of vibration phenomena. Then next, various terms used. In vibration analysis. These terms are used in vibration analysis. Periodic motion, self repetitive motion, after an equal interval of time, is known as the periodic motion, time period, time required to complete one cycle, frequency, number of cycles per unit time. Two types of the frequencies are considered, omega and f. This is in radian per second, this is in hertz. Amplitude, maximum displacement from mean position. Natural frequency, if vibratory system having no external excitation then the frequency of system known as natural frequency and denoted as Fn. Damping, damping is nothing, it is a resistance in vibration is called damping. Equipment used is called damper. System with damping is known as damped system. Resonance, if the frequency of external excitation is equal to natural frequency of system, then it is known as resonance. Due to resonance, amplitude ratio beta is unity. Next topic is degree of freedom. It is defined as number of independent coordinates required to specify a motion. Mathematically, degree of freedom is equals to 6n minus constraints, where n is number of links in system. Every link having 6 independent motion. If we are considering a 3-dimensional XYZ, then linear, angular, linear, angular, angular and linear. It means the 3 linear and 3 angular motions having each links. Degree of freedom may be finite or infinite. Finite having a some value of this, and infinite having a infinite degree of freedom. Our next topic is vibration systems. The various vibration systems are used. We are considering the systems in which first is your mechanical system. Mechanical system includes mass, spring and damper. If we are considering this, mass, damper, spring, then this system is known as a mechanical system. Continuous system having elastic member known as continuous system. This system having infinite degree of freedom. Example of this system: a cantilever beam, a fixed beam and simply supported beam. These are the example of continuous system: a cantilever beam, A fixed beam is simply supported beam. The continuous systems are also known as the distributed system. Next is discrete system, or also known as the lumped system. System with finite degree of freedom is called discrete system. The discrete system may be any kind of mechanical system with a value of the degree of freedom. Our next topic is types of vibration. Vibrations are classified. First category is linear and non-linear vibration. In this linear vibration, parts of vibration body behave linearly and they follows law of superposition. For example, if any equation is a function of this and another equation having a function of this, if the solution of this is alpha 1 and the solution of this is alpha 2, then is equals to your alpha 1 plus alpha 2. Non-linear parts of vibration body doesn't behave linearly and do not follow law of superposition. Then the vibrations are non-linear vibrations. Free and forced vibration. Free vibration if external excitation is removed after giving excitation. It is called free vibration. Forced vibration if external excitation is present after giving excitation. It is called forced vibration. Next classification is damped and undamped vibration. In damped vibration, dampers are used, then it is known as the damped vibration. Undamped dampers are not used. Next is the random vibration. If amount of external excitation is not known, and it is known as the random vibrations or non-deterministic vibration. E transient vibration. If amplitude decays continuously by use of damper and finishes finally, then the vibrations are known as the transient vibrations. Longitudinal, transverse and torsional vibration. Longitudinal vibration, if moment of mass is along the axis of body, then it is known as the longitudinal vibration. It means if we are considering this is the mass, and if you are giving some excitation, and it will move up and down along the axis of this is known as the longitudinal vibrations. Transverse vibration if moment of mass is perpendicular to axis, and it is known as the transverse vibration. If we are considering this is the axis, and if we are giving an excitation and this type of the vibration is there, it means perpendicular to the axis, then it is known as the transverse vibration. Third is torsional vibration. Bend, if you are giving a angular displacement, then bend and unbent of disc is known as the torsional vibration, or we can say twisting and untwisting of the disc. If this is the disc, and if we are giving some angular, then it will twist and untwist, then this type of the vibration is known as the torsional vibrations. Our next topic is the motion, which we are considering in vibrations. Two type of the motions are considered: linear. If our system is having a linear motion, then we are using the linear motion system, in which displacement is denoted by x, velocity is denoted by x dot, which is dx by dt, and acceleration is denoted by x double dot, dx dot by dt, or second derivative of displacement, and considering a mass which is equals to m. But if we are considering a angular motion, then the angular displacement which is equals to your theta, angular velocity which is equals to your theta dot d theta by dt, angular acceleration theta double dot, or second derivative of angular displacement, and instead of the mass we are considering the moment of inertia, which is equals to your I. So next topic is simple harmonic motion, which is a vibratory motion. Now the definition of this: to and fro motion with respect to mean position is called simple harmonic motion. And in this simple harmonic motion, acceleration towards mean position and proportional to displacement. Now if we are considering a solution of simple harmonic motion, then the displacement x is given by amplitude and sine of omega t, in which this A is the amplitude and this omega is the frequency. This is the simple harmonic motion displacement. Then we can define x dot, which is equals to your dx by dt or velocity, and the velocity is your A omega cos omega t, and if we are considering the acceleration, then dx dot by dt, which is equals to your minus A omega square sin omega t, or A sin omega t is your x, then minus omega square x double dot is equals to this. For simple harmonic motion. In this, we are also considering the phase difference. If two vectors are having same frequency, then x1 sin omega t and x2 t plus phi, then this phi is known as the phase difference. Now in this simple harmonic, we have to add, therefore the addition of simple harmonic motion, if two simple harmonic motion are added, then we get simple harmonic motion. Let us consider two vector having a1, a2 as amplitude and omega frequency and phi. Phase difference. Mathematically, x1 a1 sin omega t x2 a2 sin omega t plus phi. Then the addition of these two, the final displacement of addition is x1 plus x2 by putting the value a1 sin omega t plus a2 sin omega t plus phi, a1 sin omega t plus, using the trigonometrical relation sin a plus b, a2 sin omega t cos phi plus a2 cos omega t sin phi. Then x is equals to your a1 plus a2 sin omega t cos phi plus a2 cos omega t sin phi. Now let us assuming this a1 plus a2 cos phi is equals to your a cos theta and this a2 sin phi is equals to your a sin theta. Then x is equals to your a sin omega t cos theta plus a cos omega t sin theta, or a sin omega t cos theta cos omega t sin theta, or a sin omega t plus theta. This is the final solution of addition. And this complete method is known as the analytical method. We can also calculate this theta by using this divided by this. Tan theta is equals to your a2 sin phi upon a1 plus a2 cos phi. Therefore the theta is tan inverse a2 sin phi upon a1 plus a2 into cos phi. This is the final solution x of addition, and this is the direction of this final solution. This method is known as the analytical method, but we can also use the graphical method for addition of simple harmonic motion. In this graphical method, first step is convert all motion in same form. Second, drawing OX and OY axis. Now taking from vector x1 is equals to a1 sin omega t OB is equals to a1 at an angle of 0 degree. It means they taking this OB, which is equals to your a1 at an angle of 0 degree, then taking from vector x2 is equals to your a2 sin omega t plus phi O C is equals to your a2 at an angle of phi O C at an angle of phi. Now drawing a line parallel to OC from B and a line parallel to OB from C, a line parallel to this OC from B, and a line parallel OB from C. The intersection provides the D. Intersection is D, and finally joining OD, which is required solution. Therefore, the x is equals to your OD, the amplitude A is equals to your OD, joining this is the A, and this angle is the theta. By having this AOD and angle theta, the final solution is equals to your A sin omega t plus theta. This is the graphical method of simple harmonic motion. Now in this simple harmonic motion, we are also considering representation of SHM in complex form. Let us consider a rectangular form in xy plane. If this is x, this is y plane, and in this xy plane, let us consider a point C, which is a iota b, and this is your A O. This is your A, this is your B. Then this is the R. In this, iota is equals to your under root of -1. C is equals to your A plus iota B. But this A is equals to your R. If you are considering this angle is theta, then this is the R cos theta plus this is equals to your R iota R sin theta, or R cos theta plus iota sin theta, and this is given as E iota theta. We can also represent By using this Engg equation, we can represent a simple harmonic form motion in complex form having R, amplitude and omega frequency. Therefore, the displacement x is equals to your R, amplitude and iota omega t. This is the displacement in complex form. Velocity, which is equals to your first derivative of this, and find out the derivative of this, iota omega r e iota omega t, or x double dot is equals to your acceleration, which is the derivative of this velocity, the first derivative of this, then minus iota square omega square r e iota omega t, the square of iota from this is minus 1, therefore minus omega square r e iota omega t, x double dot. By the help of this, we can represent a simple harmonic motion in the complex form. Thank you, friends.